So we've learned about atomic mass and molar mass, right? Atomic mass is the mass of an atom. Molar mass is the mass of a mole. Molar volume is the volume of a mole. We only use this for gases. Molar volume at STP means at a certain temperature and pressure. So STP stands for standard temperature and pressure. Standard pressure is 1 atmosphere or 760 torr. It's like regular pressure, right? Standard temperature is 273 Kelvin or 0 degrees Celsius. And again, I would argue that that should be 273.15 Kelvin. So here's why I think they chose that temperature. You know, they were doing these gas experiments before the discovery of electricity, right? So how do you get your gas to be a specific temperature? They didn't have heaters and air conditioners and refrigerators and stuff. So an easy temperature to achieve is 0 because that's the temperature of ice water. So if you fill your sink with ice water and you put your your glass flask of gas into the ice water and wait, you can know that it's going to be 0 degrees Celsius, right? So that was a convenient temperature. So that's STP. And we use that to make comparisons between gases because there's those 4 parameters that can change, right? And so things could get really wacky. It's hard to compare which one is more. So STP is useful. So the molar volume is the volume of 1 mole of gas at STP. So we could calculate that. So volume is going to be NR, it's an N that turned into an R, nRT over P. So if we're calculating the gas of 1 mole, what's N? 1. 1 mole, and that's exactly 1 mole. We're saying, because we're calculating it. It's exactly 1 mole, and then R is the same as it is always. Meter atmospheres per mole Kelvin. What's the temperature?
273.
Yeah. So 273.15 Kelvin. And what's the pressure? 1 atmosphere. So if we use this full value, because the 0 is exact, this is 4 sig figs, that's 5, this is 4. So we could have 4 sig figs here. 22.41 liters is equal to 1 mole at STP. The book usually uses just 3 sig figs, 22.4. So this 22.4 liters per mole at STP is true for any gas. Because we're talking about 6.022 times 10 to the 23rd particles of the gas, molecules or atoms. So the same number of molecules will have the same volume for different gases, but the masses will not be the same. But this is a really useful conversion factor at STP. On the worksheet, there is a section, and he's got 2 or 3 questions, that's about molar volume of a gas. And you can do it the long way and do lots and lots of extra calculations, or you can do it the way it was intended for you to do the problem and just use this as a conversion factor. It's just a lot easier. Remember that this is only true for gases, only true at STP. Okay. Okay, so, don't be throwing this in where there's liquids or something, because it's not true. There's illustrations of 3 different balloons. They have same volume, 22.4 liters. This is at STP. So this contains 1 mole of helium, 1 mole of xenon, and 1 mole of methane. Same volume, same number of particles. But what about the mass of the balloons? This is going to be different. What's the mass of 1 mole of helium? 4.003 grams. And how about xenon? 131.3. And methane is 12 plus 4, 16. So this balloon weighs almost nothing, and this one's much, much heavier. Same number of particles. Because the xenon molecules are like bowling balls compared to helium's ping pong balls. Same number of bowling balls is going to weigh a lot more than the ping pong balls. But what's funny about gases is they take up the same volume. And the reason for that is there is a lot of empty space in between the particles, and we'll talk about that later. So assuming ideal gas behavior, which of these samples has the greatest volume at STP? A gram of hydrogen, a gram of oxygen, or a gram of argon? So if the volume is bigger, does that mean it has more particles or fewer particles? More particles, right? More particles would make it bigger. So which of these has more particles? The mass is the same. Yeah, it'll be the hydrogen. E2 is kind of the same. The hydrogen, you're going to get more particles in a gram because each of the hydrogen molecules is only 2 grams, whereas argon is like 40 grams. So you're going to have fewer particles in 1 gram. So this is going to be a larger gas sample. Any questions? We can calculate the density of gases. First we'll look at density at STP. So remember, density is the ratio of mass to volume. It's usually expressed in grams per liter because gases are much less dense. And so if we think about, well, if we have 1 mole of gas at STP, then the mass of it is going to be equal to its molar mass, and the volume of 1 mole at STP is 22.4 liters. It's true for all gases. So let's calculate the densities for helium and nitrogen. So the density for helium is going to be the molar mass of helium, 4.003 grams, divided by the molar volume, 22.4 liters. So 0.179 grams per liter. How about nitrogen? What's the molar mass of nitrogen?
14.01.
That's the molar mass of nitrogen atoms. So this is something that trips students up all the time, and that's why I'm kind of making a point out of it right now. Here we have nitrogen gas. It's not part of a compound. It's just nitrogen gas. Nitrogen is one of the junior high girls of the elements that never goes to the bathroom by themselves. They go everywhere with a friend, right? Diatomic elements. Horses need oats for clear brown eyes, right? Hydrogen, and then these 7 guys starting with 7 and making a 7, NOFClBri. So that's one of those things that you really do need to remember, and it's easy to forget. But nitrogen is N2, so then the molar mass is 28.02 grams. And the volume is 22.4 liters. .25 grams per liter. So under the same temperature and pressure, density of nitrogen is significantly larger than that of helium. Air is mostly nitrogen gas. So this is close to the density of air. Helium is much less dense, and that's why things filled with helium will float. Any questions? We can also calculate gas density under other conditions. And the approach I take is, let's just remember what density means. It's the mass divided by the volume. The problem will give you the information you need to calculate the mass, or they'll give you the mass, and to calculate the moles. The volume. Calculate the liters. So we can calculate the volume using a gas law. Usually it's going to be the ideal gas law. They'll give us the temperature and the pressure, and sometimes they won't give you an amount of gas. So then, like we did with other things, we can choose what we want because the density of the gas doesn't change whether you have a small amount of gas or a large amount of gas. It's a proportionality. So you can choose something that's convenient. Let's just choose 1 mole, because then that's easier. We can calculate the mass of 1 mole of the gas. That's easy, it's just the molar mass. And then we can use 1 mole in the ideal gas law to calculate its volume. So the density of a gas is proportional to its molar mass. And the book gives you this equation. The capital M here represents molar mass. And there's nothing wrong with this equation. But to use it, you have to remember it. And you have to remember that capital M means the molar mass and not the molarity or something else. And that's just a piece of clutter in my brain. I would rather just take a couple of pieces and put them together, pieces I know anyway, rather than remembering a new thing. Okay, so if you want to use that, you can, but I'm not going to do it in lecture. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. This is not STP, we can't use 22.4. Well, what are they giving us? 742 millimeters of mercury and 45 degrees Celsius. We're looking for the density. Density is equal to the mass divided by the volume. Did they tell us how much gas there is?
Yeah.
Well, they told us conditions, they told us temperature and pressure, but they didn't tell us how much. So that means we can pick. So what's easy? 1 mole. Mm-hmm. So we are going to choose N equals 1 mole of gas. So I need to find the mass of 1 mole of xenon gas and the volume of 1 mole of xenon gas. I'm going to calculate the volume using the ideal gas law. So this is my pressure. Is that unit going to work? The ideal gas law? Millimeters of mercury? No, it's got to be atmospheres. So we need to convert this to atmospheres. We end up doing this so much. So 742 divided by 760. 0.976. 32 atmospheres. The temperature is 45 degrees Celsius. change that to Kelvin. So I've got N, P, T, and I'm looking for the volume. The volume is equal to nRT divided by P. It's rearranging PV equals nRT. So we have 1 mole, and we have 0.08206 liter atmospheres per mole Kelvin times the temperature divided by the pressure check out the units. Atmospheres cancel, kelvins cancel, moles cancel. I'm left with liters. .7406 liters. The 1 mole here, we chose it, so we can choose it to be exactly 1 mole. We're not measuring that, we're just choosing it, right? So that's exact. This has 4 sig figs, 3 and 3, so this should have 3. So that's the volume, 26.7406 liters. What's the mass of 1 mole of xenon? 131.3 grams. It's on the periodic table, right? So 131.3 divided by 26.7406. This will end up with 3 significant figures. 4.91 grams per liter. Any questions?